Okay, so everyone, let's start. So today we're gonna move on to a new topic called approximate policy iteration. So here we're gonna study how we can actually leverage function approximation to deal with larger scale Markov decision process. Okay, so far, the Markov decision process stuff that we talked about, they're all like small size, discrete Markov decision process, right? Where we actually can just maintain a table where every point in the table is just a particular value for a particular state action pair, for instance. Right? But imagine now, you want to deal with larger scale Markov decision process where the number of state and action pairs is huge, right? So maintaining a table is either computationally expensive or, computation space expensive. So maybe we want to use some function approximation to approximate it, right? Like what we did in supervised learning. Right? So, but before that, let's do a quick recap. Okay, so, oh yeah, so by the way, I want to ask you guys again. So if it is possible, please turn on your camera, and I think it's always nice to see you in faces. It's also helped me, to calibrate, the pace of the lecture as well. Right, thanks. Great. Yeah, so let's recap policy iteration. So policy iteration is an algorithm that computes the optimal policy for a given Markov decision process, right? If we know the transition matrix P and R, right? The transition matrix P and the reward function R, right? And the way that we compute this is an iterative procedure where every iteration, given the column policy pi that we have, right? We compute the column policy's Q value, which is this term. And we said we can, if you recall the algorithm that we talked about for computing the Q value, we had two algorithms, right? One is the exact algorithm, where you're solving a linear system. You take some matrix inverse and solve a linear system. The another approach is that you apply some iterative, fixed point iteration algorithm to compute the value for this policy. Okay? And then once we have this Q pi, the naive thing that we could do is this one-step policy improvement, right? That's just to be greedy with respect to the current policy's Q value, right? And we prove that this operation actually gives us monotonic improvement. In other words, the new policy pi prime, the Q value, will never be, smaller than the original policy, the previous policy's Q value, right? We're always doing hill climbing, and in the homework, hopefully you have thought about this problem already. At a point that you can actually does not make any improvement, then we claim that we are done, right? In a sense that we find the optimal policy. So that's policy iteration. And the algorithm that we're going to talk about today is actually very similar to this algorithm, except that we're going to use function approximation to approximate a Q pi. Right, so the question is that if, this transition matrix P and reward function R are unknown, and the MDP is huge, right? Maybe infinitely many states, then we can't easily implement this algorithm, right? Like, remember the way that we implement this algorithm requires us to write down like something like a for loop. For all state action pair, we do blah, right? We can't, like if the MDP is large, computation-wise, we can't just afford to writing down a for loop, right? Enumeration over state action pair is not going to be possible. Okay, so then let's do a quick recap on what we covered last Thursday, where we talked about model-based reinforcement learning, right? So we talked about this important result called simulation lemma. So this basically says that if I give you a policy pi, so a fixed policy pi, but I have two Markov decision process. I have MDP1, which has a transition probability P prime and reward function R. I have MDP2 that has transition P and R. So P hat and P, they might be different, right? So the question that we are interested in is that if I hand you a policy pi, right, can you sort of quantify the difference between the performance of this policy measured under the two systems using the disagreement between the models P prime and P, right? Because these two MDPs, the only difference that they have is the difference between P hat and P, right? So this is kind of a very fundamental question, right? If you build a simulator that is epsilon close to the ground truth. And you want to understand how this epsilon propagate back to the value of your policy, because that's eventually what you care about, right? So what we proved is that we can actually nicely upbound the difference between values by the disagreement between two models, right? And it's nice in a sense that this is only averaged over the policy's distribution at a particular system, P. And so this is the state action distribution of pi under P. So think about P as a true transition, the true world, okay? The real world. So, and then we use this result to actually, model the performance of a particular algorithm, right? All right, so picture-wise, you can think about this as I'm just executing my policy pi under the real model P, right? And then along these waypoints, I'm just calculating the one-step model disagreement, right? So maybe this will be what P hat will say, right? And this is, again, P hat, and this might be P hat. Right, along these waypoints, I just check, what's the disagreement under L1 distance between P hat and P, and then just sum them together, right? Average them together, and that's, quantifies the difference between the two values, the two performance values. Right, and then, we use this result to sort of analyze a particular algorithm, which is a very simple algorithm, right? So under the generative model setting, for small discrete Markov decision process. So here, let me remind you what generative model setting means. So this means that you have the ability to reset the system to any state action pair, right? And observe the corresponding next state. So then use this property, we design an algorithm that has two components. The first component does model fitting, right? In other words, let's use the reset ability, right? So we're going to write a for loop again, because this is a discrete small Markov decision process, right? We can do that. So for all state action pair, let's reset the system to SA and observe the next state, right? And then let's reset the system back to SA again, observe the next state again, and reset, observe the next state, and so on and so forth. Let's repeat it for n times, right? In other words, we did n experiments for this particular state action pair. And now let's just do counting, right? How many times I've hit a particular state as prime. And then the probability of transiting to the next state as prime at SA is just approximately equal to the ratio of the number of times that I hit S prime over the total number of experiments that I just did. Right? So think about the coin flipping experiments, right? I need to estimate the bias of the coin. Then I can do n experiments. Then I just count how many times I hit a positive face, how many times I hit a negative face, right? The bias is just the number of times that I hit a positive face over the total number of experiments. Right? We repeat this process for every state action pair, and then we get a model, right? And now let's just do policy iteration on this model, right? And then we get a policy pi hat. Now again, pi hat, this is the optimal policy for MDP hat P and R, right? Because we run policy iteration on this approximate MDP. But now we can use simulation lemma to quantify the performance of this output policy pi hat, right? Under the real model P, because here we can use this, classic statistical tools to compute the deviation between pi hat and pi. Right? So what we said before is that you can think about there's a confidence ball where the center is P hat, it's A, and the radius is sort of square root S over N, where S is the number of states, N is the number of experiments that you do per state action wise. And we know that somewhere around inside this ball, this is the ground truth. We don't know where it is, but we know that the sort of the maximum distance between the ground truth and the center of this book, right? That's good enough because, if you record the simulation lemma, all we care is the one-step deviation, this L1 distance between the ground truth P and the center of this ball P hat, which is our estimate, right? And then you plug in this into the simulation lemma, you get a bound for the policy that you just computed, right? That's all we did last Thursday. And as I said, this concentration result, this confidence ball, the proof of these kind of stuff is definitely out of the scope, right? We don't need to understand that, but you will see this kind of 1 over square root of n rate, many times throughout this semester. Right, so that's the recap for today. So before we move on to the new stuff, any question for the recap?
So, Professor, yeah. I just had a clarification question just on the difference. So before, when we're doing value iteration and policy iteration, we're just like, it's objectively the same algorithm, just doing it like into different approaches, right? But now we're saying that we're adding in, like, we don't know the probability. Is that the difference between what we're doing now and before?
So before we know P, right? So now we don't know P. So we have to first estimate a P. And then you can use your favorite value iteration or, policy iteration, right? But keep in mind, value iteration does not necessarily guarantee hitting an optimal policy infinite number of times. But what you proved in the homework is that policy iteration, regardless of what, it's gonna hit an optimal policy, right?
Okay.
Which is nice, actually, right? Because, sometimes you want an exact algorithm, right? So, but like policy iteration gives it to you, but value iteration does not, right?
So that's actually a question. If we have the time for it, what exactly is the difference between the two? Like objectively, aren't they doing the same thing? Like
value iteration and policy iteration?
Yeah, because like value iteration is just taking R of S comma A plus the max of Q of S comma A.
Yeah.
But over here, you're just saying pi.
Yeah,
so
but remember value
iteration.
Yeah, but remember value iteration, you're trying to estimate Q star, right? So you're computing something that
I see.
converges to Q star, but you have to convert whatever your estimation is to a policy, right?
Yeah.
So it's not a direct algorithm. It's not an algorithm that searches for policy. It's an algorithm that actually computes the values to approach to Q star. And then you have to do extra work to get the policy.
Got it.
Right? And that's why you probably do not get a monotonic improvement. But policy iteration, think about this as a hill climbing. Like every time you switch to a valid policy,
a different
you guarantee
policy,
the policy is better.
Got it.
Right.
Can I ask a question about that?
Yeah.
So in value iteration, we're just we keep updating the Q, but we don't infer anything about pi until the very end, right?
Yeah.
But in policy iteration, we keep updating the pi, and that's always better. Okay, got it. Thank you.
Yeah.
So, and for this, the model-based RL, are we going to be training based on is the plan basically to use the approximate P that we have and then put a bound on the error with regards to the optimal policy for the real distribution? Is that the aim of it? Okay.
Yeah. Okay, great. All right, so let's move on. So as I said before, from today, we are more interested in large scale Markov decision process, right? So when we face extremely large state space or continuous state space even, right? So enumerating all possible state action pair does not sound like a, doable option, right? For instance, for this game Go, the total number of unique border positions is larger than total number of atoms in this universe, right? We can't even we can't enumerate. We just can't enumerate, right? So this causes a problem in either computation or space or even statistics, right? Imagine that we run the previous algorithm that we just talked about. We have to reset it to every possible border position and take an action and observe, the next state, which depends on the opponent, right? So we just can't do that. We're gonna need infinite many samples to do that. So what we should do if we are facing such kind of situation? Right? So the answer is, let's try to use function approximation to achieve generalization. Right? So maybe we can use linear function approximation, we can use decision tree, or we can use supported vector machine, or nowadays, people use nonlinear neural networks. Right? But these are function approximation that takes some state, some input and output something, right? And we're trying to generalize across these examples.
Are we vectorizing the state to represent some sort of information like the linear quadratic? Okay, cool.
Yeah, we will get to that. Yeah, we will get to that. Yeah, that's a very good point. And I actually want to mention the LQR again, right? So LQR, as you said, the state is in RD, is in Euclidean space. And there we actually have infinite many states, right? But what we did is actually we parameterize our Q function and value function, use polynomials, right? Our value function, V star, I'm not going to call it X, let's call it X, is X transpose P, X plus this little p, right? So in other words, we can just remember this D by D matrix plus this scalar. We just needed to remember D squared plus 1 parameters, right? And then we will be able to compute V star at every possible state. Right? We don't need to maintain a huge table, infinite size table for that, right? All we need is just remember the parameterizations. Right, that's what we did, for instance, for linear regression, right? We just maintain we just remember the parameters of the linear regression, linear regressor. All right, so another example is, let's see, we want to apply reinforcement learning on this, very old video game, right? So here a state is an RGB image. So here, potentially if you change a pixel, you're going to get a new state, right? So there are many, many states. I don't want to, maybe there are like 84 times 84 because the pixel is like 84 times 84. And every pixel I have 255 unique numbers, right? Because this is RGB image. So my state space is huge. But what we could do is we can try to capture Q star via some neural network, right? An example is that let's just use some convolution neural network, right? And the input to this convolution neural network is a state and an action. So here the state is just an image. Let's just feed this RGB image to this convolution neural network, right? And maybe somewhere along the last layer, let's just append the action information. Maybe let's just factorize the action as well. Maybe if I have 4 actions, let me just parameterize the action as, using this binary coding, right? I can parameterize the action using 0, 0, 0, 1, 1, 0, 1, 1, right? So then I just feed this information into the neural network again, and hopefully the output approximates, Q star, right? Of course, we know that there might exist some parameterization, right? Some values for the parameters in this neural network can approximate Q star. Right, but our job is to find these parameters, right? To learn these parameters.
Are we trying to estimate Q star or P? That is another question, because in some cases, aren't both technically? Sorry.
You can, yeah.
Like Q star is the reward function, right? But before we were just talking about estimating P.
Yeah.
Is there a difference?
So estimating P, so estimating P is doable. But estimating P is harder, right? Because you need to approximate the distribution. But here you just need to approximate a scale, right? So estimating P is called model-based methods. So if you are designing a method that directly estimating Q, then it's called model-free, right? So in a lot of cases, you want a model-free algorithm because predicting from high dimension inputs to a scalar is easier than predicting a distribution, right? Getting the distribution correct is harder because the distribution could live in high dimension space.
Got it.
Right? Like we always want to do like regression or classification. Classification is even easier than regression, yeah, because we only care about maybe finite number of classes.
So then how do you train this? Because you don't actually have Q star, do you?
We don't, we don't. You're right.
So then
we haven't get there yet.
Supervised. Oh, okay.
We haven't get there yet. Yeah, you're right. Like I can't even get an unbiased estimate of Q star, right? Because it's optimal policy effect. Yeah. No, we haven't talked about any algorithm for this yet, right? So the Q learning will be one approach to do that. We will get there. Yeah. All right, so yeah, so let's summarize the question for today, right? And the next few lectures. So how to approximately learn pi star using function approximation, right? And we're trying to solve larger scale Markov decision process for now. And remember that enumeration over state action pair is not feasible. All right, so here's the outline for today. So let's do a very quick recap on supervised learning. Right, and let's revisit classification and regression. And then let's move on to this algorithm called approximate policy iteration. Right, and there we're going to use regression as a black box oracle for this inside this algorithm. All right, so let's recap supervised learning. So let's start from classification. Right. So you've probably seen this image before. So I have a training data, right, that consists of ID examples, where each example have an image about the cat or dog, and I have a label. Right, and then using this training examples, I can fit a function approximator. So here, maybe I use Gaussian process, I use a decision tree, or I use a neural network. Right, so I get some nonlinear function approximation. And then I can actually make decisions on the image that I have never seen before in the training time. Right, that's the power of supervised learning, right? And we train something on a finite data set, and then we predict reasonably well on something that we have never seen before. So in other words, we use function approximation, we're able to predict on something that we never seen before, and we call this the ability to generalize. Right, so that's the hope of function approximation, right? Because there's no hope we can sort of enumerate all possible cats and a dog in this world in order to do classification, right? It's just not possible. But what we hope is that if I have reasonably large enough data set, maybe my function approximation is able to predict reasonably well. Of course, we will suffer some error, right? It's not perfect. It's never going to be perfect. But we can do reasonably well on something that we have never seen before in the training example. Right? And once we get done training, all we need to remember is this function, right? The parameters of these functions. We don't need to remember the data set. Right? In other words, we don't need to make a table where each entry of the table corresponds to a cat or dog. Right? We just remember the parameters. And an example is maybe regression. So here I'm making up a very contrived example. So here maybe the x-axis is distance to Whole Foods, a Whole Foods market. The reason that I pick Whole Foods is that we don't have Whole Foods, and I kind of miss Whole Foods. And the y-axis is the value of a house, right? Okay, so maybe you guys don't buy this example. So let's just change Whole Foods to school district, maybe. I mean, we have Trader Joe's now, so it's not so bad. All right, so now the story is a little bit more realistic. So if my house is more closer to school district, then maybe the value of the house is slightly larger, right? So I do a lot of survey, I get these data sets. Right? And we could just fit a linear regression, right? A line on it. And now we can actually make prediction even on a house that we have never seen before in the training example. Right, so let's maybe formalize the regression problem a little bit more. All right, so I have a data distribution D, and where I get a sample xi from this distribution, and then my regression target yi is sampled from this ground truth function, right, which is unknown, plus some additive Gaussian noise. Sorry, not Gaussian noise, plus some additive noise where the noise has mean 0 and has bounded range. Right, so this, I'm just describing a way to generate the training data. And we want to approximate f star using finite number of training examples, right? So let's just make the problem more abstract. Let's just introduce an abstract function class, this call f. where every function in this function class is one of the candidates that we're going to use to approximate f star, right? So think about this cal f as a function class that contains, all possible 10 depths decision tree, right? Or, this function class contains all possible 3-layer, ReLU parameterized feed-forward neural network, right? It could be infinite. And let's just do least square using this abstracted function class, right? So the least square says that over all possible, 10 depths decision tree, let's find a decision tree that minimizes this sum or square loss, right? And let's not worry about optimization problem. Let's just assume that we have some good optimization oracle that returns the minimizer. So this is called empirical risk minimizer, right? It's an empirical risk because we're using the finite number of samples to approximate the expectation. Right, so this argmin corresponds to the optimization algorithm, right? So if you're using neural network to parameter this f, maybe you're gonna run stochastic gradient descent, right? And if you're using SVM, this is a convex optimization problem, so you can actually find the exact empirical risk minimization, right? For least square linear regression, we have closed form solution, right? All right, so the question is, what's the quality of this ERM f hat? Right, we have done so much work. We get a training data set. We try our best to find the best candidate among this abstracted function class that minimizes this sum of the square loss. What's the quality of this f hat? Right, when I actually tested it in the under new examples. So if you recall the learning theory that you touched in the intro to machine learning class. Right, so we can actually say something about the performance of this ERM. So more specifically, if you recall the VC theory, we're not going to go through the VC theory again, and it's okay that you forget it. We're not going to need that in this semester, right? So let's see, we have this ERM f hat, and we can actually say something about its prediction performance when testing it under the same distribution D. Right, the same distribution D. And that's if we assume that this ground truth f star belongs to our function. So this means that there exists one decision tree that it can actually universally approximate f star very well. Or there exists one neural network that can actually approximate f star. But we don't know what it is, and our goal is to find it, right? And we can say that reasonably well for the performance of f hat, the ERM. So basically, we can see that the expected prediction error, the L2 loss between the L2 distance between my prediction f hat from f hat and the ground truth f star, and this expectation is bounded by some small number delta. Right. So this number often shrinks in the order of square root of 1 over n. Or sometimes it could be faster in the rate of 1 over n. Right, but these are the details of the statistical analysis of a supervised learning algorithm, which is something that we don't want to go into the details in this class. All right, so just give you some quick example. So if my f hat contains all linear functions, right? If my f contains all possible linear functions, where the parameter theta is from a ball with radius w, right? So we can say that this delta can be roughly around w over square root n. Right, so I can guarantee that if I have n training examples, the expected prediction error of my best least linear function f hat and the ground truth f star is around w over square root n. So that's how the prediction error is going to shrink. Or I can show that this is in the rate of d over n, where d is the dimension of theta. Right, so you can actually show two types of bounds. So, I mean, I'm just giving you an example, and how we get to these bounds, these are out of scope, right? So the first bound basically says that I can actually do infinite dimension linear regression as long as my weight vector is bounded, right? So that's why kernel works, right? Because kernel is infinite dimensional stuff. And kernel works because we can actually get these kind of bounds. Our bound only depends on the norm of our predictor, right? So it could be infinite dimension. And the second bound gives us faster convergence rates, but the price that we pay is that you have to pay this dimension d, right? So if you're dealing with low dimension linear regression problem, that's great. You get this very fast rate, right? D over n. But if you are dealing with infinite dimension stuff like like ridge kernel regression, ridge kernel linear regression, right? So you're going to use the first bound. So that's actually why kernel works, right? Because we know that kernel actually is infinite dimensional stuff, and we cannot apply, for instance, things like VC dimension to it because VC dimension is infinite for kernel, right?
Wait, sorry, what was theta again? Sorry, I think I missed that.
Yeah, so the data is we have some underlying distribution D, right? And then the training data is sampled from this distribution. So you sample an X from this distribution, and then you observe a noisy output, right? So F star is the ground truth. So F star is the ground truth. It's unknown. You want to approximate it, right? But you don't get to observe the exact thing. Maybe there's some observation noise or whatever, right? So you observe the F star measured at xi plus a little bit of noise. Right, so that's the data set you get, and you get like xi, yi from I equal to 1 to n. Right, so this is some data set that someone hands to you.
You're saying the labels might not be completely accurate. They have a little bit of noise.
Yeah, so here it's not even a label, right? Imagine the regression problem where like you try to
regression. I mean, yeah, I don't know the word for it, like the output or.
Yeah, we can call it regression target or something. Yeah. Right, but the noise is zero mean, right? So that's important. So that's why I put this assumption here. It's zero mean, right? And similar things applies to classification, right? So in the intro to machine learning class, you probably talk about VC dimension for classification, right? So you can actually get sort of a bound. So if you still recall VC dimension, right? So for classification, for binary classification, we kind of can show that our arrow of our f hat is around square root of VC dimension of our function class over n. Right, so if you remember VC, that's great. If you don't remember VC, just think about this as, the sort of all the possible labels that you could get on a given data set. Right, so I give you a data set, you apply every function in function class f, and you get a label, right? Like how many unique labels you could get. So we know that for finite dimension problem, the VC dimension is like d plus 1, right? So think about 2D cases. You can only sort of, like your VC dimension is like 3 in 2D cases, right? You can only shutter, at most 3 points. So in other words, like if I have 2D space, I have examples, looks like that, right? So there's no linear classifier can perfectly classify them, right? But if you have an example that looks like that, then there exists a classifier that can perfectly classify them, right? So that's the VC dimension. So in other words, if you're doing classification in 2D, you can shutter 3 examples, any 3 examples, right? I give you any 3 examples, you can find a function, a linear function that classify them perfectly. But if I give you 4 examples, for example, this example, right? Positive, negative, negative, positive, you cannot find a linear function that perfectly separates them. Right, so that's the VC dimension. You know, if you still recall it.
Yeah, that makes sense.
Right, so that's, you know, the sort of the general picture that we should keep in mind about supervised learning. Right, so the details of these rates, we're not really going to care that much in this lecture. But keep in mind, you know, this delta is small and it shrinks in the rate of 1 over square root of n. Right, the more examples you give to it, you know, the smaller this prediction error is. Right, so an example, not example actually. So I want to talk about at what situations supervised learning can actually fail. Right, so the case where it fails is you have distribution mismatch. So if you're trying to learn something under this training distribution, and if you're trying to test what you learned on this test distribution D prime, that is not necessarily equal to D. Right, then we potentially will be toasted. Right, so here the video is not working, but here I'm trying to show, I was planning to show you this video where this robot keeps falling down, right? And I try to estimate the dynamics of this robot using the falling down data. And I want to estimate the dynamics of the robot walking. That's my goal, but I'm not be able to get the data about the robot walking. All I have is the robot constantly falling down. But let's look at this particular, you know, naive examples, right? So this green curve is the function f star that I'm trying to approximate. For some reason, I'm not be able to get training data across this entire axis. So this is x, this is y, right? All I have is these training data. So my training data is coming from a very constrained subspace interval, all right? But I can get many, many training data. But unfortunately, they just constrained in this small interval. All right, I can fit some function m hat, you know, that can achieve tiny, tiny training error on these training examples. Right, so you can do really well on the examples that you have seen so far. You can use linear classifier, you can use decision tree, you can use neural network, whatever, whichever is your favorite, right? So if in the test time, I give you the same examples from this interval, then we can expect that we can do well, right? Because that's supervised learning theory tells us. If your examples is coming from the same training distribution, which means that it's very likely that it's coming from this constrained subinterval, then we know we can do well. But if today I tell you this new training example, testing example, sorry, right? The testing example that is widely different from the training example, there's no hope that we can ensure that our predictor can do a good job, right? Because you have never seen any examples outside of this training region, right? Right, so this problem applies to any function approximation you use, no matter how deep your neural network is, no matter how big the data set is, right? So in other words, you know, there's no black magic in this, right? So everything is governed, you know, by the rules of math, statistics, and optimization, right? It's just like we don't have any information about what's going on outside of a training region, right? There's no hope that we should be able to there's no hope that we can predict it well. Right, so in other words, you know, when we talk about transfer learning, we have to be very careful, right? We needed to introduce additional assumptions in order to say that this is successful. Right, maybe your ground truth here, f star, is indeed a linear function. Then maybe I can say something, right? Because in order to fit a d-dimension linear function, I might just need d+1 examples, no matter where they're from, right? As long as they're different enough. But who knows? Maybe my f star is like 10th order polynomial or 20th order polynomial. Who knows, right? I'm just using linear function to approximate, or I'm using like neural network to approximate. Yeah. So in other words, when you talk about transfer learning, we need additional assumptions. Right. Otherwise, it's too good to be true, right? Right. So distribution match and distribution mismatch is actually a serious problem in reinforcement learning, right? Because we train something, we get a policy, and when we test this policy, we ultimately gonna get a different distribution, right? Because we hope that our policy is better than the previous policies that we've seen. But better meaning that we actually visiting some different states, action space, right? By collecting higher rewards. So you want your policy to be better, but then you inevitably see something that is different from the previous distributions, right? And you want to make sure that whatever function approximation that you're using from the previous iterations can actually do well on your new distribution, right? So that's the challenge of reinforcement, because this is not a supervised learning problem anymore, right? The data is generated from the policies that you trained, and you want to keep improving your policy, which means that your policy is inevitably visiting different state action pairs, right? Right, so let's recap on supervised learning. Let's make a regression as a particular example. So throughout the semester, we're often gonna just assume supervised learning succeed if there is no distribution mismatch, right? So we're not gonna worry about the details of optimization. We're just gonna assume that we can minimize this empirical risk, the sum of the square loss, right? How we minimize it depends on, the parameterization of my function f, depends on the optimization algorithm that you use, right? Later on, we were going to talk about a stochastic optimization approach, which is SGD. We're going to prove that it's convergence for convex function and converge to local minimum for non-convex function. But for things like SVM, decision tree, we have algorithms corresponding to this argument, right? And SVM, everything's convex, so you're good to go. Just do whatever convex optimization program. Right, so we're not going to worry about how to get this. Let's just assume that we can approximately get this f hat, this empirical risk minimizer, and let's just expect that we will have small test error under the same training distribution. Right, under the same distribution where you get the training example. So in other words, under the same distribution, our prediction error measured in the same loss will be small. So delta is a small number. Think about this as shrinking in the order of 1 over square root of n, or sometimes even 1 over n, right? Depends on the assumptions on the models. But the bottom line, we can do well under the same distribution that we use to generate the training data. And as the number of training data goes to infinite, this prediction error goes to 0. Right, so any question for the supervised learning part? So the reason that I'm spending that much time on the supervised learning, because I want sort of everyone to get on the same page where like how we get this generalization ability by using function approximation, right? So we can actually guarantee prediction error under the expectation, right? Which means that we can actually probably do well on the examples, test examples that we have never seen before in the training example, right? So we don't need to remember every possible, cat, dog image in the world. All we need to remember is the parameters for this empirical risk minimizer f hat. All right, so next we're gonna move on to reinforcement learning again. We're going to see an algorithm that uses regression, the least square regression, as a computation oracle. Right, so one of the general philosophy of solving reinforcement learning problem is to say if we can reduce reinforcement learning problem to supervised learning problem. right? Because we know how to solve supervised learning problem, right? It's a very fast moving area. People developing new neural network architectures, people developing new optimization algorithms for optimizing supervised learning, right? So if we can somehow build a reduction framework from reinforcement learning to supervised learning, then whatever new advancement that we can make on supervised learning will be translated to the advancement of reinforcement learning, right? So that's one philosophy to solve reinforcement learning problem. And indeed, if you look at those programs that DeepMind wrote, those AlphaGo Zero, whatever, they actually follow this philosophy. So they convert reinforcement learning problem into many sub-supervised learning problem. And on that, they use classic neural network architecture plus SGD, stochastic gradient descent, to optimize, right? All you need is to transfer whatever the output of this regression or classification back to the reinforcement learning problem. And you want your reduction to have the following property, where if you have better performance on supervised learning, this better performance is translated to the better performance of reinforcement learning, right? So that's the dream, but we're not really there yet. All right, so now let's forget about supervised learning, right? Let's get back to this infinite horizon Markov decision process again. So this is same notation, except that now you should not think about this SA as some small, discrete sets, right? So a particular state could be huge. And here I'm just going to introduce an initial state distribution mu0. In other words, the first time step, the state is always sampled from this distribution. Right, so this is like you play in video game, the initial configuration of the game is roughly, fixed, right? Right, so let's recall this state visitation, this state probability. So this is the exponential averaging over the time-dependent state distribution, right? So this is the probability of you visiting this particular state S at time step H if you follow policy pi, starting from this initial distribution mu0. All right, so for this algorithm, let's consider the following parameterization. So we want to estimate Q values. Let's just design a function approximator, a function class that contains many functions that maps from state action pair to a scalar from 0 to 1 over 1 minus gamma. Right, so this might be a neural network that looks like this. The input is S over A. So somehow, we vectorize this state. If S is an image, let's just vectorize it, right? Because you just put, these pixels values into a non-vector and also append the action information on it. So if you have discrete number of actions, we can just binary encoding it, right? For LQR, your control, this U is action A is also from a Euclidean space. So we can just, concatenate SA together and feed it to a neural network. Right, so that's our abstracted function class. Right, and of course you can replace this neural network by decision tree or Gaussian process, whichever one you want, right? Yeah, so example is like all 2-layer neural network or all 10-layer, regression tree or all possible linear functions, right? All possible maybe linear functions in kernel space. Right, so we're gonna relax the generative assumption. So here we're only gonna assume that we can reset from a state that is sampled from the initial state distribution, right? So we play a game, we either lose or win, but we can reset the next game from the initial state configuration, right? And the S0 sampled from this mu0. Right, so this is a much weaker assumption than the previous generative assumption, right? The previous generative setting assumption says that I can reset to any state action pair I want. So here I'm saying that you can only reset based on the initial state distribution, right? You can only, start driving your car from your garage or, some parking lot in the campus, right? You'll not be able to reset your car to any XY position in the world. Right, so this is a much more realistic assumption. This is sort of the weakest assumption that we can hope. right? So that's the setup for today.
I have a question.
Yeah.
So if we're gonna prove some bounds on the estimated Q function, is it dependent on mu0?
Correct. Yeah.
Okay.
Yeah. So we're not going to prove anything for today. So we're just going to go through the algorithm and we will see like what's going on in this algorithm next lecture.
Got it. Thank you.
Right. Because there's two sort of important concepts that I want to talk about today, which is how we get training examples. Right. We'll not be able to write down a for loop. So we can only sample state action pairs from some distribution, right? We can only sample some regression target as well. So how can we actually design sampling oracles to get training examples? All right, so in high level, this algorithm just behaves like policy iteration. So we iterate between two steps. So let's try to find some function approximator. So this is from this Q class, right? Let's maybe find something in our function class that can approximate Q pi t. So pi t is some of our column policy. So think about policy iteration, right? Every iteration we have a policy, we run this like linear, like this matrix inverse or whatever to compute Q pi t, right? If we know that the transition operator P and R, if the problem is discrete, a small number states. But here, we are facing unknown transition and reward, and we are facing, large scale MDP. So we might just can only hope that we find some function approximator Q hat that approximates Q pi t, right? So if we believe that this approximator is good enough, let's just follow the policy improvement step that we had in policy iteration, right? Let's just be greedy with respect to our estimator Q hat. And in the extreme case, if Q hat exactly equal to Q pi t, then this is the monotonic improvement of policy iteration applies here too. Right? But that's an extreme case that's too nice to be true, right? Yeah, so basically here we're going to use supervised learning, specifically regression, to estimate this target Q pi t. Right? But there are two questions left, right? So this framework looks pretty simple, right? But two questions left. How we can actually get training examples? Like we need to get training examples here, right? Because this is reinforcement learning. This is not supervised learning. No one hands a data set to us. Like we have to create data set for ourselves, right? And then what's the quality of the learned? If we get data and we do least square, then what's the quality of this learned function approximator Q hat? Right, so these are the two questions that we needed to sort of understand before we can analyze anything about this algorithm, right? Right? Any question for the general framework? Okay, so today we're mainly going to focus on how to get the training data, right? Because that's important. We're going to use this process, data generation process, over and over again in the next few lectures, right? Like this is kind of fundamental because this is reinforcement learning, right? We need to get data by ourselves. Like no one's going to give us a data set.
Professor,
Yes.
just a question before we start.
Yeah.
Are we assuming that S and A are finite or?
No, we're not assuming that. Yeah.
Okay, we're not. Okay.
Okay, so so for this algorithm, A will be finite for the purpose of this operation, right? Because argmax, is defined over a discrete set. So for this purpose, let's assume A is finite because otherwise this is not computationally efficient, right?
Do you need it to be finite though? Like, I mean, you can still do the derivative
conceptually,
over
yes.
the Q prime. Like the
Conceptually,
Q
we
arrow.
don't, right? Conceptually, we don't. But let's just make our life easy, right? So let's just say that I have a discrete number of actions I can enumerate in order to find this argmax. Right? So if you have continuous action space, you can discretize it, then you enumerate, for instance, right? All right, so let's talk about how we get training data for running some supervised learning algorithm. So the first question that we want to ask ourselves is, how can we actually get a state action pair, SA, from this distribution? So while you think about this question, let me just rewrite the notation of this distribution. Right, so remember, this is an infinite mixture. So if you recall how we get a sample from a mixture distribution, so imagine I have a Gaussian distribution P1, I have some other Gaussian distribution P2, and my mixture distribution is something like 1 minus alpha times P1 plus alpha times P2. Right, so these kind of mixture distribution that we learned in Intro to Machine Learning, right? So this is like how we actually run, like how we actually interpret clustering algorithm, right? How we actually do like EML algorithm, for instance, right? So if I have this mixture distribution, how we get a sample from it?
Should there be a gamma to the H term in the summation or no?
Correct. Yes. Sorry.
Okay. But to answer your actual question, can you just, well, I guess you want to sample from each distribution in the mixture, but they're kind of dependent on each other, right? Or are they?
Yeah,
So maybe can you just sample like one path? Is that valid?
yeah. But remember, this is a mixture distribution, right? So think about this example. So I want to sample a point from this mixture distribution. So I have weight 1 minus alpha on P1, weight alpha on P2. Like P1 and P2, they could be dependent with each other. It doesn't matter, right? So what I can do is, let's first flip a coin to decide which distribution to pick. So maybe I will pick P1 with probability 1 minus alpha and pick P2 with the rest of probability.
Oh,
right?
I see.
Flip a coin, and I first decide which distribution I want to sample. So if the coin determines that if I want to pick a sample from P1, then I commit to P1. Then I just call the sampler for a Gaussian distribution, right? So in our case, this is a similar situation, right? Like we have, so for now, forget about the trajectory distribution, whatever. For now, just think about this as an infinite mixture, and every distribution has some probability of being sampled, right? The probability of being sampled is gamma to the power of h over times 1 minus gamma.
So can we just keep flipping a coin until, or like generating a random number between 0 and 1 until it's less than gamma, and that'll give us the mixture we're sampling from?
Yeah, so or you can just sample a time step h with probability gamma to the power of h over 1 minus gamma.
Right.
Right, so you can implement this like in Python or MATLAB, right? So this is just like, so you just write down the probability vector and ask it to sample an integer.
How do you sample this? If you're only allowed to reset to S0 in mu0.
Yeah.
When you
Here
have
I'm
to
just
actually
sampling a time step, right? I haven't get to the state action pair yet.
Okay.
So here I'm just convinced you that I'm just talking about a sampling procedure for mixture distribution, right? First, I need to pick a distribution to sample, right? So here, let's see, I flip a coin and I committed it to this particular time step h. All right, so now I want to get a sample. I want to get an SA sample from this distribution. Right, so now your question applies, because I can only reset to mu0. Right, I cannot just arbitrarily get a state action pair at time step h, right? But what I can do is I just start from some S0. I just execute a policy all the way to time step h, and then I throw away all the previous samples. I just maintain the current state action pair at time step h. Right, so you should convince yourself this is a valid sampling process, because this term is the probability of hitting a state action pair. Right? If I follow pi from the initial state distribution mu0. So picture-wise, what we are saying, right? So first step, let's sample a time step h. This is corresponding to pick a distribution from the infinite mixture distributions. Right? And then we committed to a time step. Let's just try to get a state action pair. So the way that we have to do that is to reset the system to S0. Which is sampled from this initial state distribution. And then let's just execute a policy pi all the way to time step h, and then we just return this SA pair. Right, so that's our sampling procedure. That's how we get a sample from this infinite mixture distribution. All right, so any question for this procedure? Okay, great. So the next question is a little bit more complicated. Let's see if you all will get confused. All right, so the question is very simple. So given that we are at state action pair SA, how, and a policy pi, how can we actually get an unbiased estimate of this value, Q pi SA? Okay, so again, while you're thinking about this problem, let me just write down the definition of Q pi SA again. Right, so this is just expected total reward if I start from SA and follow policy pi. Right, so how can I get an unbiased estimate of this if I'm already at SA and I know the policy pi? All right, so let me just tell you one naive approach, right? Which is, let me just start at SA and then just execute pi for infinite many steps, right? So then I get reward along the waypoints, and let's just sum them up using this exponential weighting, right? So this is R0 plus gamma R1 plus gamma square R2, so on and so forth, right? And if I can do infinite many steps, if I roll out my policy from SA infinite many steps, and I sum them the reward together with the corresponding weighting, then this should be an unbiased estimate of Q pi SA, right? Because this is just a particular sample. In a sense, I get a particular sample trajectory, and then I sum the rewards together, following the weighting, the exponential weighting rule, right? So this should give you an unbiased estimate of Q pi SA. But the problem is that you have to roll out for infinite many steps, right? Because this is defined over infinite many steps. Like we can write a program that, do infinite many steps.
Can you do a finite horizon approximation?
Yes, you can, but that does not give you a unbiased estimate, right?
Actually, I have a question about this. Isn't it possible that you make the action in the first step and then you get trapped in some area, and then that expected reward in that area does not reflect the overall expectation?
Yeah. So that could happen, right? So all I'm claiming, this is an unbiased estimate. If you take the expectation of this whole process, it's equals to Q pi, right? But one sample could be very off, right?
Mm-hmm.
I see someone raise their hand. You want to unmute yourself and ask a question?
No, not question, just to answer this question. So can we just do like Q pi from the start and minus the previous step up to S? Because for all the strategy is the same for the Q pi from the start. So basically we just compare the subtraction of the S0 to S. Does that make sense?
0 to S. But you still need to get this infinite trajectory to get.
Oh, I see.
Right?
Yeah.
Okay, so let's see how we can do it. It's a bit tricky, but I think at the end, in hindsight, we will like this. I think it looks pretty interesting, right? But at this stage, you should convince yourself that if I'm willing to do infinite many steps throughout, then I'm done, right? I get an unbiased estimate, in the sense that I can repeat this process infinite many times, compute the average, then this average approach to Q pi SA, right? Yes, as someone said, if I just repeat this process one time, due to unluck, whatever, I might get a very bad estimate, right? But Nevertheless, if I repeat many times, take the average, this approach to the ground truth that I want to estimate, right? So this is the same issue of the coin flip, right? So if my coin is biased towards positive face, if I just flip it once, I may well observe, the negative face, right? But nevertheless, this is an unbiased estimate, right? Because tomorrow you repeat it again, you may see the positive face, right? The day after tomorrow you repeat it again, you're going to see another face. But if you do it many times, you take the average, you're going to approach to the ground truth.
Wait, actually, could we do something where you sample it and then you keep on going until you hit the same state again? And then
so you will never hit the same state, right? Imagine the state space is right. So imagine you do Gaussian distribution sampling. What's the likelihood of you hitting the same sample? It's zero, right? You're never gonna sample, like if you can sample state from Gaussian distribution, but you're never gonna see the same state.
Makes sense.
Right? Unless you do discrete distribution sample. So the trick here is that let's actually think about these weights as a mixture, like as probabilities again, right? So here I'm just doing something like exponential weighting over the reward function, the reward at different time step. So maybe I can sample a time step and just terminate there and sum the reward together and return this number. So that's our hope. Right, so let me just describe the algorithm and then let's just draw a picture. All right, so let me just start from SA. Okay, so this is the initialization step. Let me start from SA, and then for h equal to 0 all the way to infinite, let's receive a reward function. So remember, here we start executing our policy from S0, A0. All right, so if I'm at time step h, I'm going to receive this reward signal. All right, so then with probability 1 minus gamma, let's just break the for loop and return the total reward that I've collected so far. All right, so every time step, I flip a coin. I'm going to determine if I'm going to continue or I'm going to break. If I'm going to break, then I'm going to return the total reward that I've collected so far from the beginning of this process to the current time step. Right? So one thing that you need to notice that there's no discounting factor. Right? So this is kind of magic, but we will see why this is true. Right? If I don't break, then let's just move on. I sample the next state from the transition, and I sample the next action from my policy. Then I repeat. Right? So picture-wise, we start from SA at time step h equal to 0, and we keep repeating this process. We keep generating the next state following our transition and the next action following our policy pi, but it's just every time step, let's do a coin flip, right? So maybe at time step h here, with probability 1 minus gamma, I decided to terminate this process, right? If I terminate, I'm just going to return the sum of the reward along this partial trajectory. Right, so this is called a rollout process. The previous process that we saw is called rolling because you just execute a pi from the initial state and you roll in until a particular time step. So this is kind of the rollout process, right? All right, so this is the algorithm description. It's kind of magic. Let's think about why this gives us a reasonable unbiased estimate, right? We have 5 minutes left. Looks like we're not going to get into the algorithm, but let's just get this correct, right? So the claim here is that one rollout gives me an unbiased estimate. In other words, if I take the expectation with respect to this random output y, this should equals to the thing that I want to estimate, the ground truth Q by SA. All right, so let's do the proof sketch, right? So let me just ask you this question. So there are many events, right? So every event corresponding to a particular time step where I terminate. So the first question is, what's the probability of we actually terminate at the very first step and return y equal to R0?
One minus gamma.
Yep. And what's the probability of we actually do not terminate in the first time step, but we terminate at the second time step?
Gamma times 1 minus gamma.
Yes. So now you can see that there are many events, and each event you can calculate the probability, right? And then each event corresponds to a return value. So in other words, we can just write out the expectation, right? This is the probability of we terminate at h equal to 0. And this is the value we return if this happens. This is the probability we terminate at the next time step. Right? You know, what's the situation this thing happened, right? I don't terminate at h equal to 0, and I terminate at h equal to 1. So the probability of this event happens is gamma times 1 minus gamma, right? Because the probability of not terminating is gamma. So you can do the same reasoning for time step h equal to 2, right? The probability that we actually terminate at h equal to 2 is that we don't terminate in the first 2 steps, but we terminate in the third time step. So the probability is gamma squared times 1 minus gamma. And the return value is this, right? So if you write out this infinite summation, if you rearrange in terms, I promise you will get this term.
So I just have a question with regards to practicality. Like for this, wouldn't the time taken to even get a small data set be insane? Like, because even this, it's the expectation that gives you QPy rather than just the value itself, right?
What do you mean?
Then you have to at least run it a few times. Like you can't just run it once and assume that's correct, right?
Yeah. So remember, so do it multiple times is not feasible here. So you cannot reset it to particular state action pair and repeat the process.
Exactly. So then how do you do this? Because this theoretically will give you a value, but it's the expectation of the value that is QPy, not the value itself, right? So you have to take an average, right?
Yeah. So remember for linear regression, we never assume that the training data, the regression target in the training data is the exact value computed by the ground truths, right? There is noise. As long as the noise is 0 mean, then when we have many examples, these noises sort of cancel with each other, right?
So if you take multiple examples at some point, you'll just,
Yeah, because for this example, I may observe a positive bias, but for the second example, I may observe the negative bias, right? In expectation, the bias is 0. All right, so let's just summarize this data generation process, right? So remember the goal is I want to get an SA pair from d pi mu 0, and I would get a scalar y such that expectation of y equals to q pi SA. Right, so we're talking about this 2-step process, this rolling and roll out process. Right, so we can apply this rolling process to generate a state action pair. And then at this state action pair, we apply this roll out process to generate an unbiased estimate of our target Q pi SA. Right, so in other words, let's just do this rolling and roll out process. This gives us a triple, which is state action pair and the corresponding estimation of the Q pi SA. Right, so wait, where is my picture? Okay, so now we can repeat this process n times, right? So let's do n rolling in and roll out process. So now we get a training data set that consists of n examples. Right, so here Si, Ai is from d pi mu 0, and the expectation of yi is equals to q pi Si AI. Right, so now we can get a data set. This data set looks like a regression data set to us. Right, if we train a function that predicts from SA to Y, then hopefully this function can predict the Q pi SA, because my regression target is an unbiased estimate of my Q pi SA, right? So my claim is this is a regression data set.
Is there this is, so is there like a bound on the time complexity of this process? Like,
yeah, you can bound this in high probability. So in worst case, you can still stuck in infinite steps, right? Because what if the worst case happens? Every time step you flip a coin, it says you don't terminate. That could happen, but what's the probability that happen? Exponentially small, right?
no, so overall, as in both roll in and roll out together,
Yeah,
is there a bound?
You can do, yeah, you can bound it in high probability. I mean, the reason it's a high probability because there's tiny probability if you are stuck with infinite many steps, right? But the probability is like exponential small. All right, so I think I'm gonna stop here because I think this is this rolling and roll process is a sort of a new concept. I think we should try to digest.